welcome to Module 11. This is going to be sort of a case study. So this is going to be just a walkthrough of a particular use case in which we are looking at flights, airline flights, movies being played on airline flights, how to choose which of the latter to play on which of the former, and we'll use some of the tools we've seen in previous modules. So for now, we assume that you've already completed Module 7 to 10, and you can basically load small CSVs using pandas. You've seen .lock to identify elements of data frames. You've seen Boolean masks, you've seen the group by function, and you've seen a simple pivot table. So by now also you should be more and more comfortable with running notebooks in Jupyter or potentially VS Code. You have some basic Python plotting experience. Mostly this has just been sort of what I've provided so far, but you've at least seen some plots using matplotlib, and that you're, like, so far we've been focusing on intuition and just usage of the tools, and we haven't yet got into like any kind of advanced statistics or machine learning yet. By the end of this module, you should be able to take this kind of vague problem, this vague kind of product question, and turn it into some concrete operations in the pandas library. You'll be able to take two different tables and join them and do some basic sanity checks. We'll build decision-ready summary tables and plots, so you'll see more and more examples that we've seen previously. You'll be able to choose and defend simple metrics that can match sort of what the use case or the scenario expects or demands. You'll be able to name at least two risks or potential biases, even in this relatively simple case study analysis, and that'll help you do similar sort of risk naming in the future. So the big idea in this small little module is that really working with pandas basically is about connecting rows in tables, those are data points, to actual decisions that you're going to want to make. And then doing so, you're going to have to trade off costs of different types. And it's not just about kind of following, like painting by numbers and just following steps and getting some kind of graph out of it. It's always, everything we're doing in data science here is towards some ultimate purpose. So the scenario here, what we're going through is basically trying to figure out which movies to play on which routes. Okay, so we work at an airline, and we're in collaboration with the Halifax airport, and we're planning departures from the Halifax airport, and we want to basically optimize a couple of things. So far we have flight logs, so we have information about delays, routes, so where the airplane leaves, where it lands, what airlines are flying on these routes, and overall satisfaction scores on these flights. We also have a movie metadata, so this includes genre, like drama or comedy, runtime, how long it is, and some external ratings. So we have like a rating from some internet database of movies, for example. And the stakeholder, the people we're kind of working with on this data analysis process is, well, directly we're talking with the in-flight experience lead. So there is some lead of a team, and then they want to make sure that the experience in flights are as positive as possible, so that the passengers give the highest satisfaction scores that they reasonably could. So our decision right now, working with the stakeholder, would be hypothetically here: should we pay extra to license longer movies on long-haul routes out of Halifax? There's short routes, and then there's long routes across the country, for example. So already, as usual, we have sort of costs of error. Okay, so like either we pay for longer movies, and we don't actually need them, or we don't pay for longer movies and we should have gotten them. So both of these have different costs of error. So in the first case, we have false positives. This is where we think longer movies will help, but they don't. So we wasted all these license fees. Maybe there's some other problem like delays, and the delays is much more correlated with satisfaction than just movies played on flights or available on flights. Another cost is false negatives. We think longer movies do not help. Like no one's going to care if they're going to watch a long movie, but in fact, if we had implemented that, then actually we could have improved satisfaction on key routes. So each of these have different kind of costs associated with them. So we want to follow this kind of repeatable pattern. So this pattern of these 5 steps is more or less the same kind of 5 steps we're going to take in a lot of different kinds of tasks. Obviously the stakeholders are going to change, the specifics of the data are going to change, but high level, we can walk through the same sort of sequence on a variety of problems. Okay? So the first step is really to understand the stakeholders' problem in their language. Okay, you're going to find that you're going to work, depending on where you work, with like domain experts who have their own particular ways of working on problems. So again, I work mostly in healthcare settings, and healthcare settings have their own language in terms of disease and diagnosis and treatments. And different cost structures and different procedures that we might not have in computer science or engineering. So it's important to understand how to communicate to the stakeholder. And basically, like in this, this is a very simple case. There's not too much translation we have to do. We understand that they just want to see if, like the stakeholder wants to see if, certain kinds of movies should be played on certain kinds of flights out of Halifax. Once we have that, generally we go on to the filtering phase. This is where we kind of like take all of the data available and narrow them down to the relevant rows. So I don't care necessarily about flights going from Calgary to Edmonton or vice versa. We're really focused on flights from Halifax or YHZ. Then we start grouping. So we look at the comparison units, like what are we actually looking at, which variables are the ones we want to attend to. In this case, it's things like route and airline and like movie fit. We'll talk about that in a moment. Then we aggregate, we compute summaries, we do some statistics, we do some means and counts and proportions for all of these different groups. How many routes are there? How many movies do we have? How often do these things correlate with one another? And then there's a couple of steps missed here. So like typically the step between step 4 and 5 might be actually some modeling, but we're going to get to that later in the course. But it's very easy as you're moving through these steps, even in the early pre-processing phases, to produce some visualizations. And visualizations can be in the form of tables of numbers, or nice plots, or even just text, like paragraphs, descriptions of what we've found so far. So in this study, we're going to use 2 tiny realistic tables directly in Python. We're going to construct them in Python. Flights, this is 1 row per flight. We're going to have an origin, a destination, airline, the airtime in minutes, the departure delay minutes. So how long was the departure delayed? The arrival delay, how long was the arrival delayed in minutes? We're going to have movies played and then satisfaction provided by the passengers. We also have a separate data set, a movies data set, in which case we have like 1 row per movie, okay, like movie type. When I say movie type, I mean like not an instance of the movie being played, but just like the actual title of the movie. Okay, so we have movie ID, title, its genre, its runtime, and its rating from this movie database. So the units are going to matter. So delays will be in minutes, not hours, for example. If we were measuring departure delays in hours and arrival delays in minutes, this would be sort of something we'd have to kind of fix up. Here, it's pretty straightforward. If the delay is negative, this is sort of, it's early. It happens occasionally. I've been on some flights that have actually arrived early, so a negative delay just means it's early. Satisfaction is not measured on like a scientific unit. It's measured on a Likert-like scale. You can read more about what a Likert-like scale is over here at this link. But basically, a Likert-like scale is one in which you have like a range from say 1 to 5, like 1 being the worst, 5 being the best, and then people kind of give a score in terms of whatever they're asked to rate. There's a whole science around Likert scores and how to how many elements do we have on this list? Is it 1 to 5? Is it 1 to 10? How do you describe what each of these things mean? That's a whole other story. And runtime is also going to be in minutes. So here is fictional data, and as usual, I kind of create this this big list of elements. I put these elements into a data frame using pandas, and then I'll just store that in a variable called flights. And because flights is a data frame, it has the function .head, so I just call flights.head, and out come the first few rows of data here. Okay, so you can scroll through it, look for anything out of the ordinary, and hopefully nothing should jump out at you. This is the movie data metadata, so the same kind of setup. We have rows of data here, and I feed them into a data frame, and then I use head to just see the first few rows of this data frame. You might want to, when you copy and paste this into your Jupyter notebook and you want to play around a little bit, you might want to just see what happens if you add some kind of errors here, right? So like forget to include a quote, for example, or forget to include a colon. Maybe forget to include an entire number or an entire field and its value. Right, so just try to make some problems. Okay, like that's one of the best ways to learn is to take something that works and then fiddle with it until it breaks, and then and that can teach you something about like, well, why did it break? So that when you're in a situation when you're coding up your own data set, your own code, your own project, something goes wrong, you've already seen that kind of error in your experience. So go ahead and try to break this. So this is the kind of what we're trying to accomplish. We have the raw flights data. We join the flights data with the movie data set. Then we create some features. So we have already data in these data sets, but we can combine them and we can compute some extra statistics from them. From that, we're going to produce summaries by just doing some grouping, and then we'll make some decisions. Okay, pretty straightforward. So here's kind of one of these anti-examples we're going to have quite often. This is kind of a failure mode where we're just going to ignore useful information, and we're kind of just stuck on the idea that, well, the only thing our stakeholder wants is graphs, right? They ask for a report with graphs in it. Graphs are pretty. Graphs give the appearance of actually having done any kind of work. So we're gonna mimic a data scientist's activity by just producing graphs. So imagine you go ahead here and you take your movie data set, you sort your movies by the IMDb rating, you say ascending equals false, which basically means it's descending, so starting from the highest values and then sorted down to the lowest values available. Plot it as a bar graph, provide a title, etc., etc. Here's matplotlib. There we are. Matplotlib allows us to add a Y label, IMDb rating. Here it appears on the left. I allow a tight layout. This is just sort of a formatting thing. Produce this graph. I mean, it's a graph. It provides us with some information. It tells us that the movie Pacific Horizons has the highest rating in IMDb of the movies we have available, and Snack Attack has the lowest one. It visually might demonstrate a little bit of how different the top score is from the lowest score. But this is not great because, like, sure, movies are part of our decision scenario. We want to understand what movies we're playing on what flights, and we want to play good movies on our flights. But we're ignoring everything to do with flights at this point. All we're doing is fixated on one variable. The stakeholder is not going to be that pleased with this kind of feedback. The problem is we're just optimizing these external IMDb ratings. Maybe movies appear. People have a different appreciation of movies when they're cramped in a little airplane seat than when they're sitting on their couch at home or when they're in the movie theater. So these ratings might not actually refer to how much people like movies when they're in an airplane. There's no guarantee that this top-rated movie will be a good fit for a short regional hop. If Pacific Horizons is like a 3-hour movie and the flight is only an hour and a half, then who cares whether or not Pacific Horizons has a high IMDb rating? And there's not really any kind of decision metric that we can make, right? So again, the whole point is to provide analyses that our stakeholders can use and then actually implement something in the real world and ideally make the world a better place, even if it's just a matter of choosing movies on airlines. And so far we've done nothing to help. So it's going to be much better to connect every plot we make and every form of communication we make to the stakeholder, that make sure that it helps them make a decision, that there's some kind of signal that they're going to care about in our analysis. So just again, we talked about this at length already, but you can't do data science without doing science, and you can't do science without math. And math and code are very closely related, and both of them are equally as practical as the other. Okay, there's nothing more practical about just knowing how to code or what functions are available in what code library. There's nothing more practical about that than knowing what the code is actually doing, like fundamentally, like what are these steps taking care of. That's normally described formally in terms of the math. So if you don't understand what's going on, that is to say, if you don't understand the math that describes your problem, then you don't understand the problem, you can't solve the problem, you can't solve things practically. So I'm going to emphasize this over and over again. Some people just have a difficult time accepting the idea that math is fundamental and it's important and it's part of the practical exercise of data science and machine learning. They think it's something theoretical that is purely abstract, but I want to just make it absolutely clear that that's not the case. So the math here, fortunately, is not going to be very complicated. What we want for every route, we want all of its flights, and we want to compute kind of on average the arrival delay in minutes. Okay, so this is something that's described to us in plain language from our human stakeholder, the person we're working with. And the formal definition is going to be something like, well, we can define a variable, just like we define a variable in Python. We'll call this d sub I, and this will be the arrival delay of flight I on route R. So we only care about routes R within this analysis. So here's, we have n sub R. This is another variable we define. This will be the total number of flights on that route. So what is the average delay, arrival delay in minutes for flights on this particular route? Super easy. We just take down here, it says this, all of the routes are, say from Halifax to Montreal. I, and this E is an element of, so for I being an element of that set, that is to say, for all flights that are on this route from Halifax to Montreal, we have a delay for that flight. For every individual flight that goes from Halifax to Montreal, we just sum up over all of them, and we divide by the total number of flights on that route. And this should be as no surprise to you. This is the mathematical representation of the average arrival delay in minutes. I'll represent that down here. This bar at the top of D sometimes is used to represent the computed average of something. So D bar sub R just means the average delay on the route R. So in this next example, it's Halifax to Toronto, to Pearson Airport. So we only have 5 flights measured between Halifax and Toronto. The first one has 10-minute delay, a 0-minute delay, a 70-minute delay, a 0-minute delay, and the last one is 5 minutes early. Okay, so just summing up over all these delays is a total amount of delay of 75 minutes. And there's 5 flights, so 75 divided by 5 is 15, and we're good. So on average, a flight from Halifax to Toronto is 15 minutes delayed. We're going to implement this with a couple of steps now, group by and mean. So here we are. This is a bit of fancy Python code that might be a little bit complicated, but we're going to basically get a single variable called flights. This will be from the dataset flights. We're going to assign the route. The route is a function, and lambda says this, what follows is a function. The function takes a data frame as an argument, and all it does is it takes the origin, like the column called origin from the data frame, and then it concatenates with plus this space dash space string, and then concatenates that with the destination string from the data frame. Okay, all this is going to do is create like a lot of strings that have the origin code dash the destination code. Actually, I think I said there's a space here. There's actually no space between the double quotes and the dash. So here, once I have all of this, I have my flights, which is all my data set, and then I have this this route column. I can group by route. So it is group by does what it says it does. It takes all of the instances of a particular route, and it measures the arrival delay in minutes. Okay, so there might be several instances of YHZ-YYZ in the data frame flights. It'll just group all of those together. And then it'll also group together all the instances of YHZ-YVR into another group of elements. Okay, and I'm only looking, when I'm saying group by, I'm only doing this grouping by according to the route variable. I still want to measure something, so I'm grouping by route, but for every route I want a measure of some quantity. The measure of quantity I want is the arrival delay in minutes. This is one of the column headings I have in my data frame. You can go back and check. And I just specify it by using these double quotes, and I tell the data frame that I want the values, so I pass that into these square brackets. So far, I have flights.groupby, so I have these groups of data grouped by route. You imagine different kind of sets or different silos of these arrival delays in minutes, and every group represents a different route. Within every group, I'm now going to call the mean. So the mean, for every group I have a list of elements, compute the mean over those list of elements. Then given those means, and given all of that data, resetting the index just helps me draw the table. You don't need to know this. And then I want to sort the values according to the arrival delay in minutes, and I want to have descending, start with the big, ascending to be false. So that's descending, so start with the big delays, and then sort in descending order. The biggest delays, the next biggest delays, and so on. So a little bit complicated. I'm basically just chaining together a lot of operations on a data frame. So I start with the raw data frame. I get the groups. I group by route. I get I care about this particular value, the arrival delays in minutes. I get the means within every group. I reset the indices, and then I sort those means that I computed on line 7. And then line 12 here just prints it out on the screen, which is what I get over here. Okay, so I had these groups, and the average delay in minutes from Halifax to Toronto was 18.33 minutes in my data frame. Now I can take the route delays and I can plot them. I can just plot these averages as bar graphs. The X's are going to be my routes, those groups I just had. The Y's are going to be arrival delays in minutes. These strings actually don't necessarily have to be the exact same string values that we had previously, but you can play around with this also. Try to break this code. I changed line 1. Regardless, I create a horizontal line of value 0. It looks like a dashed line. I set my Y label, I set my title, I set my tight layout, and then I show the graph. And now I have this graph. So now I have information about the different routes that I have. Every route will have many flights. The average of those flights per route are shown here in this graph. So the delays to Toronto are longer than the ones to Vancouver, which are longer than the ones to Montreal. So, which route is the most delayed on average? It's the one with the biggest bar graph over here. You can ask yourself, what is the average delay in minutes? Hopefully this won't be hard for you to determine from this graph. Does this line up with your intuition? So you might assume that flights that are longer might be more likely to have delays than those that are shorter. Montreal is the closest to Halifax of these 3 cities. Vancouver is the furthest. So does this distribution of averages make sense to you? Is it surprising? If it is surprising, how would you How would you kind of think about looking into this problem? If you want to now make a decision and say, well, it's bad if an average delay is more than 15 minutes, do any of these flights need attention? If so, which ones? So we're going to do some feature engineering now. So feature engineering is basically taking the data that you already have and then computing some extra statistics on top of it that might be more tied to your decision-making process. Okay, so we can define a new feature. This feature we're going to call runtime_gap_min. This is the total number of minutes spent in the air minus the runtime of a movie in minutes. Okay, this is the difference between, like, if you're in a flight, how much time could be spent in a flight where there's no movie playing, if there's one movie that you can play on a flight. Okay, so the overall airtime minus the runtime of a movie is the amount of time not watching a movie on this particular flight. If it's negative, then the movie is going to be longer than a flight and will get cut off, and that's something that the passengers might not like. If it's close to zero, it's closely matched, and if it's largely positive, if the airtime in minutes is way longer than the runtime of a movie in minutes, this is a lot of extra time. After the movie ends, that the passengers might be bored. I presume that they should have books with them anyway to read, but that's another story altogether. So here's some code. We're going to take our flights data frame. We're going to merge it with movies. How do we merge two data sets? I'd advise you to look into the merge documentation, but essentially both the flights data set and the movies data set have this movie ID variable in them. So you'll kind of join those together, and that's how you're going to merge these two data sets. How are we going to do that? Towards the left. So now for every combination of flights and movies, we want to have a new feature called runtime_gap_min. What is that feature? Well, it's just this computation over here. So this is in brackets. You could put line 6 up on line 5 and dispose of the brackets if you wish, but this is just maybe a slightly more readable way of providing this computation. This is just implementing what I mentioned a moment ago. Take the air time in minutes from the flights movies data set, subtract the runtime minutes from the flights movies data set, and store that in a new variable called runtime gap minutes, which is our very simple engineered feature. So now I want to just take a quick look at my data again to make sure nothing weird is happening. I want to look at flights movies. I want to see the flight ID, the route, the title, the airtime in minutes, the runtime in minutes, the runtime gap minutes, which I just computed a moment ago, and I still want to see satisfaction. So satisfaction of the passengers on this route is going to still be important to me, so I'm going to include that also. And here is this is my big data set. So you can see, lost it. There we are. So we have, the route, the movie that played on that route, the airtime in minutes, the runtime in minutes, and this gap I just computed, which is the difference between those other two quantities. Does this actually matter? So does the what we just computed actually mean anything? We're going to see. Okay, so we're going to kind of take the gap we just computed, and if it's less than 0. Again, that means that the movie is longer than the flight, which means the movie is too long and it would get cut off. Otherwise, if the gap is not less than 0, so it's some positive number, the flight is at least 1 minute longer than the movie, then we can say, well, if the gap where there's no movie playing for the passenger is less than or equal to 60 minutes, this is kind of a good fit. I mean, modern passengers might not get too bored just staring at the seat in front of them if they only have to do so for 60 minutes or less. Otherwise, if that's not the case, then that means there's at least 61 minutes of spare time, and this could be considered, according to our breakdown, as too long for the passengers to be sitting there doing nothing. So I've defined this decision rule as a function. So everything from line 1 to line 7 here is a function. The keyword def defines that it's a function. I have a space. I have the name of the function, bucket underscore gap. And then everything in this parentheses is going to be just a variable name. It could be whatever you want. That basically says I expect there to be an argument passed to this function, and I'll call it gap within this function. And then colon basically says that everything indented under this line, under line 1, is going to be part of my function. So everything from line 2 to line 7 will be part of my function. And then I already walked through the logic a moment ago, but you can satisfy yourself that that's what this function is doing. Now I have my flights movies data frame, which I computed a moment ago. It has the runtime gap minutes, which is my engineered feature, which I inserted into the data frame a moment ago. Data frames allow you to run this function called apply, which takes as an argument a function name. Okay, so what this is basically saying is for every element of this vector defined as flights movies runtime gap minutes, apply for every value in that column, apply the function bucket gap to that value. So everything that I'm highlighting over here, that'll be a vector of numbers, like a list of numbers. You'll take the first number in that list. I'm not sure what that is at the moment, but actually I'll go back. It would be 30, okay? So take that number and pass it to the function bucket gap. So, and you hop into this function. Now gap is equal to 30. I go to line 2, is gap less than or equal to 0? In other words, is 30 less than or equal to 0? No, that's not true. So skip this condition, go to line 4. Otherwise, is gap less than or equal to 60? That is to say, is 30 less than or equal to 60? Yes, it is, right? So therefore, because that's true, I hop in here down to line 5, and I return the value, the string, good fit, 0 to 60 minutes to spare. This function returns, and for that element of that list of numbers, I'll now have a string associated with it, which is good fit space 0 to 60 minutes spare, which I'm going to store in the first element of a new column in flights movies. That column will have the label gap bucket, and I'll just have these strings returned for every element in my list will be put into this this column. Okay, I truly advise you to, if you want, go here and between lines 9 and 10, print out a flights underscore movies square brackets string gap bucket close string close brackets, and satisfy yourself that each of the elements of this new list of strings is associated correctly with the number we get from flights movies runtime gap minutes. Okay, so I want a summary. I still want to help our stakeholder make decisions. So now I'm going to jump in and kind of go through the same kinds of sets or descriptions that we saw a moment ago. We have flights underscore movies, my data frame. I want to group by this gap bucket, these labels that I just assigned on line 9. And for every bucket, whether it's lots of spare time, a good fit, or way too long, I want to just see what the satisfaction measures are. Okay? Remember, the satisfactions could be on a scale of 1 to 5. So now I have different silos. Every silo is all of the data associated with one of the possible strings in gap bucket, which are one of these strings returned by the bucket gap function. And I have satisfaction scores for every one of those elements. I then want to aggregate over those that data. I want to do 2 aggregations. I want to do a count, and I want to do a mean. Okay, so aggregate sag function on line 14 can take a list of strings, which just tells that aggregation function what kind of aggregation we're doing. So count is one of the possible aggregations. Just count the number of instances of data in that bucket, in that group. And mean is take the average score among those elements. I can take the mean here because satisfaction is a number, so you can take a mean of a number. you might want to, again, play around with this a little bit and see what happens if the variable that I'm tracking in each of my groups is not a number. Maybe it's a string, right? And then if you try to take the mean over a string, see what happens. Okay. Reset index is just a convenience, and then I want to sort values. I want to sort the mean values I computed. Again, ascending is false, which means it's descending order, so big values on top, small values at the bottom. So yeah, there's the gap summary I just computed a moment ago. I have 5 instances of lots of spare time. So in the group with the label lots of spare time, there are 5 instances of flights that fall into that particular gap bucket. And then the average satisfaction score is 4.54. There are 6 instances where the difference between the flight time and the movie time was a good fit. So there's about 60 minutes of dead space of no movie being played, 6 instances. And in those cases, the average satisfaction score of passengers on those 6 flights was 3.9-ish, and so on. We're starting to get some information here now. So you can now we're starting to relate flights and movies in terms of a measure of those types of data, in this case just the lengths of flights and lengths of movies. We've grouped things together, and then we've computed satisfaction scores in each of these buckets. So now we're starting to get something which is much more resembling a decision that a stakeholder can make. Like before, we had the anti-example where we just had the ratings of IMDb movies, sorted, but that didn't relate to anything to do with flights at all. But at least now we're kind of combining movies together with the flights, and yeah, we're making some progress. So it's very slight here, but you started to see that there seems to be a bit of a signal, right? So the lots of spare time when there's no movie playing, it's a pretty high satisfaction score, as might be the case given today's movies. But when you have movies that are too long and have to be cut off, this is associated with low satisfaction scores. Is this meaningful or not? Is this only a coincidence? Maybe this is a correlation only, like it's only a coincidence? Well, it's yet to be seen. Anyway, down here we just plot the results that I just computed here a moment ago in gap summary, and then here we see them. This is just a visual representation of these numbers I saw a moment ago. So we have something in a table, something in a plot, and so far so good. So looking at this, which of these buckets look best to you, and would you recommend, based on this graph, changing movies on any particular route yet? Or is it still, is the sample too small, or do we have not enough information to start making decisions at the moment? I want to point out that earlier with our anti-example, we also had a bar graph with these blue bars of descending heights, and superficially that looks similar to this. Someone who doesn't understand anything about analysis or data science would say, well, why is one bar graph an anti-example, a bad example, and another one, this one, a better example? I mean, we talked about that a moment ago, so hopefully it's obvious, but ask yourself that question as well. So before we trust our summaries, we have to always check a couple of things, okay? So are there any routes or movie fit buckets with only a small number of flights? Okay, with only 1 or 2 flights might be too few examples to make any massive changes to our airline. Are there any data that this seem unrealistic? Are there any values for for delays that are just not really plausible, like a delay of minus an hour or something like that, or more than 3 hours? Are any of the satisfaction scores outside of the range of 1 to 5? Okay, so we kind of just jumped into at least some level of analysis, but all of these sort of sanity checks or quality checks are going to be important to run initially also. Look for any obvious data issues. Are there any duplications? Are there any impossible combinations of delay and satisfaction? And then the route level flight counts add up to the overall number of flights in our sample. Okay, so we'll talk about pre-processing and data sanity and other modules, but this is always something we have to be aware of. So we want to choose metrics that match our decisions. So for our entertainment lead, or for our user experience lead from the airport, there's a lot of measures they might care about. There's the on-time performance at all, so they might care about the proportion of flights with the arrival delay in minutes being less than or equal to 0. Those are flights arriving on time. Maybe a flight that's only 5 minutes late can still be considered to be on time also, so maybe the 0 could be a 5. This is something that you would discuss with your stakeholder. What is the satisfaction gain on long-haul flights? Okay, so is there an average, before a change computed on satisfaction? Is there an average before a change is made? Is there a difference between the before and after of some change being made? This is a delta in satisfaction. So, does that matter at all? What is the fraction of long-haul flights that get a good fit movie? So maybe, it's not only true of long-haul flights, short flights also. We saw a moment ago that movies that get cut off are associated with low satisfaction scores from customers, from passengers. But you might, when I look at long-haul flights, you might worry about passengers sitting there twiddling their thumbs and not reading books that they forgot to bring. So how many flights actually have movies that fit the length of the flight, and how many of those don't, for long-haul flights, for example? What are the costs of error? So if a decision is made to change the movie on a particular flight, is there a risk of overreacting to noise in a tiny sample? Maybe there's only one instance of a flight from Halifax to Calgary, for example, one flight in your data set, and all of the passengers on that flight had low satisfaction for some reason. And then therefore you decided, well, there must have been some effect of the movie played on that flight or available on that flight that made them dissatisfied. But maybe there's some other reason for that dissatisfaction for passengers from that flight. Maybe there's grumpy to begin with. You don't necessarily know that, so don't make decisions based on weak evidence. And indeed, fixing movies on just the Halifax to Montreal flight, might be trying to put a Band-Aid on a Band-Aid on an arm when someone's leg is missing, so to speak, right? So maybe the real problem is that the delays are the problem, and then the main effect on satisfaction is delays, and has nothing to do with movies or how long the movie is relative to the flight. So, just keep that in mind also. So you always have to ask, the metric might look great. You might have computed something that seemed reasonable at the time, but does this actually help you take actions that has some material effect on whatever it is you care about, i.e. satisfaction in this case? And what kind of mistake would be the most costly? So even in this kind of example of satisfaction of passengers on flights, it might seem less consequential than, say, healthcare decisions. But it's also very realistic. So a lot of us will end up working in this sort of scenario where the main use case is making our customers or our passengers, or whatever the customer segment is, happy. So as is the case in this example, and in the case in the real world, satisfaction surveys can underrepresent some passenger groups. So imagine the surveys are only available in English. Imagine that they're worded in such a way that is confusing to people for whom English is not their first language. It's going to disadvantage. You're not going to have enough data from certain subpopulations of your passengers. Maybe some of the passengers are just tired of filling out surveys. For whatever reason, there's a subgroup of people who have a ton of surveys to fill out, and they're going to not fill out your particular survey in a way that is as fulsome as you might like, and therefore the data is noisy in some way. Optimizing movies for average satisfaction might also neglect other kinds of issues. So are subtitles available for people who don't have typical hearing? Are there audio descriptions? So this is something that we kind of totally ignored in our analysis a moment ago. The response rates and satisfaction by route and demographic could be taken into account. So you could go a bit deeper into the data and you could try to expose issues related to the language of the person who's flying, information about their demographics, other informations about routes. See if like I mentioned a moment ago, in general, people who fly between Halifax and Calgary just might be less satisfied than those from any other Canadian city. Has nothing to do with movies. Something else is going on here. You include accessibility requirements is always important. So explicit constraints, will be something. It's not just nice to have. You have to take it seriously. And any kind of assumptions you make. So we assumed lots of things during our examples. We assumed the breakdown in terms of what constitutes a good fit between movie length and flight length. Usually this is between 0 and 60 minutes, but maybe it should be between 15 and 45 minutes. Like why did we choose those particular numbers? Why did we choose exactly 0 minutes to be the cutoff to determine whether a flight is on time or not? Why did we not look into other kinds of features we could have computed during our feature engineering step? An awful lot to consider. So document all your assumptions whenever possible. So next, this is only a mini case study, so we didn't really learn any new tools here, but it's always important to kind of go through examples and take the code and, again, copy and paste this code and run it yourself, try to break it. Always important to do that kind of work. So this is kind of a scaled down version of the kind of work you're going to see on assignments in this course, but also in your projects in real life. So, again, this is not just something to listen to in a video, like actually do the work and get experience with this code, simple as it is. You can go ahead and you can do this. We're going to increasingly through this course stop using synthetic tables and use more and more larger real world, bigger, messier data sets in other kinds of real world scenarios. We're going to add different kinds of features. So here we just did, we looked at the differences between timings, but maybe time of day is important. Maybe people who have to fly at 4 in the morning are grumpier than those who fly at 1 in the afternoon. Maybe the aircraft type has a strong effect on satisfaction. Maybe the different passenger segments is something we could have tried to get information on. Maybe a third data set we could have included and joined together with our first 2 data sets. We're going to go deeper into visual storytelling, so I'm very excited about that, but kind of how to build dashboards and reports for non-technical stakeholders. And we're going to use tables like these and visualizations like these as inputs into actual predictive models. We're going to do some training. But generally, the core pattern is going to be the same. We're going to start actually with kind of a vague question. And the vague question will be, the answer to that vague question will be somewhere in these raw logs, in the raw data. The first thing we're going to have to do is clean up that data. We kind of skipped over that in this use case, but we're going to see a lot more of that in future modules. Cleaning the data, summarizing the data, plotting information from that data, and then using those plots to help make decisions. Here, as always, are your quick checks. Please go through these questions, write down your answers, and bring them to class. Looking forward to seeing you in the next module.